Okay, so finally, and I hope this will be shorter than the other two segments, but the flux integral is going to be not f dot t, but f dot n ds. Okay, now what is f dot n and why do we do this? First of all, the word flux has to do with going through something, right? So the idea is this: if this is your c, if this is your curve C, and if the vector field is, let's say, working like, at this point, if the vector field is like this, um, how much of, see, so the vector field F is representing like the flow of um, some energy like heat or radiation, or it could be, physical things like water or some kind of an air or some kind of gas flowing across C. C could be your mask you're wearing. C could be some kind of a membrane or a filter or something, right? And the point is, if, oh yeah, maybe I should draw another one. If F is parallel, okay, then nothing is going from one side to the other, side A, side B, nothing is flowing across C, right? So at this point, the amount going from side A to side B is zero. But at this point, something is going from A to B. How much of the thing is flowing? And that is, the answer is, it's a normal component. All right. So if this is N, you take the normal component of F, and that's the flow across from A to B at this point. Now, if you have a vector field, uh, well, defined at every point on C, you can do this at every single point. All you have to do is to calculate for each point not the tangential component like in the work integral, but the normal component, all right? And if you find the normal component of F at every single point, then you can start adding them, i.e. integrating them. So when you integrate the normal component of the vector field, normal component of the vector field F at every single point, okay, you will get the penetration or the amount of things flowing from one side A to the other side B of the curve C, and that is flux. And so hopefully it makes sense for you to know that the flux is the integral of F dot n, because F dot n is the normal component of this, okay? And so that's pretty much it. And it turns out, just like in the tangential component work integral, you no longer have to find the speed, which usually involves the messy square roots, okay? You don't have to find r prime. Let me show you what's going on here. Oh, by the way, I think I said this in winter, but I mean before, but in the winter time, the sun is at a lower angle, right? And so the sun comes in like this, the sun's over here as opposed to way up here. And so what happens is the normal component of these is much smaller than the summertime when the sun is higher, okay? And so the amount of heat absorbed at every single point of the ground in winter when the sun is low is much less than the summertime when the sun is high. And that's why the total amount of heat absorbed by the ground, which is basically the flux of the heat energy on the ground, is much less than in the summertime. Okay, so that's one reason that summer is hotter than winter. Another reason, of course, is that the daytime is longer in summer. All right, so you don't need to have this. Okay, but let me explain then how you do this. All right, so if I have, let's draw this in C. If this is my curve C, right, and you know where the tangential component is. Tangential component is this, okay, and the normal. Let me go ahead and try to do this more precisely. Yeah, okay. I will draw a little better picture so I can explain this better. All right, so the tangential component goes along the tangent. So this is capital T and this is capital N, right? Now, let's say this is dx dy. It's basically this times dt, okay? That's what it is. All right, so that's the tangential component. Let's say this is like, just for the sake of illustration, this is 3, 2. Okay, if t is 3 comma 2. What is n, the normal component? Well, you know that there's a right angle between these. So this thing here, the normal component will be 2, negative 3. You see that? If t, the unit tangent vector is 3 comma, well, it's not unit tangent vector. Maybe I should just make sure that this is, actually, this is not t here. T, yeah, all right. So it's supposed to be t dt here, but let's just do, just use capital T. If this direction is like 3, 2, then the normal component has 2, negative 3. So the point I'm trying to make is, in order to find the x and y coordinates of capital N, if the tangential component is x, dx, dy, this will be dy comma negative dx. I hope you can see this. If you turn this 90 degrees, this is what you get. Or I should say, from here to here, it's the negative 90 degrees, because the counterclockwise is the positive. And so that's the difference, all right? So what used to be dx dy is now dy negative dx. And I will try to use that to explain what's happening here. Remember, this can be written as pq time dot, okay, what's n? Well, n, so t used to be dx dy, but now n is dy negative dx. All right, so that's what this is. You can rewrite this, and people use this notation. It's negative q dx, because you have negative dx times q, plus p dy. Okay, so that is the flux integral. I know it's a little confusing, but another way of writing this is negative qp. So you switch the order and make the q negative, dot it with dx dy. Okay, so that is how you can evaluate the flux integral. Maybe I should give you one more explanation before we do an example. All right, so the conclusion is that the flux integral, which is not as as simple as the other one, the flow integral, which is f dot t. Okay, so this is actually going to be this. It's the integral of negative q dx plus p dy, or as I said before, it's negative qp and dx dy. But another way of saying this is this, okay? So you know that if t, here's the thing, okay? If this is your tangent vector, and if this is the normal vector, now you remember, if you just have anything normal, it doesn't have to be unit vector. You can rewrite this as dy minus dx. That's what I was trying to illustrate here. Okay. Now, if you were trying to normalize this, then you would have to actually do something more different. It's more careful. Dy dt, dx dt. Oh, sorry, it's negative dx dt. And then you have to divide this by the speed, which is dy dt square plus dy x dt square, right? And so just watch what happens here when you integrate this. Okay, that is f dot, this whole thing, okay, dy dt comma negative dx dt all over the square root of dy dt square plus dx dt square, right? Now that's what n is, but what's ds? You remember what ds is? It is the magnitude, well, it's r prime, the magnitude of this times dt. So you can use that. It'll be dx over dt square plus dy dt square, and you take dt here. But just like, with the work integral, this and this go away. So it turns out this is simply pq dotted with dy negative dx, and then dt stays out here. And so that is pretty simple, right? And so let's now do an example of, or maybe example or two, of flux integrals. All right, so here's an example. Let's say my vector field G is x, y, okay? And C is the unit circle. And you know how you define the unit circle or parameterize the unit circle, right? It's unit circle, by the way, means we talk about the unit circle. It's a circle centered at the origin with radius 1. So parameterization, the simplest parameterization, the most common one is cosine t sine t, as t goes from 0 to 2 pi, okay? And you should be quite familiar with this, this parameterization. I'm going to draw a picture, and then I am going to ask you to find the flux of G across C. See, because flux is going from one side of the other, we say across a curve. And then the work done by G along or on C. Okay, and I'll clarify what I mean by this, but let me draw a picture and then I will explain what these things mean. Okay, let me go to the second one here first. Okay, so what is the work done by G as you go from this point, because T goes from 0 to 2 pi, you're going to be navigating around the circle and come back to the same point 1, 0. All right, so what happened? The work done by G is obtained as follows. It's F dot dr. Okay, you could also write this as P dx plus Q dy. I think this may be easier. So this is G, by the way. Okay, and you know what G is? G is just x, y. Parameterized, if you use parameterization, this is cosine t comma sine t. And then dr, or I should say r prime, is simply, and you take the derivative of this, it's negative sine t cosine t, right? So if you integrate, if you take the dot product of these, okay, you actually get, you see what that is? Negative sine t cosine, so here, negative sine t cosine t plus sine t cosine t, and you get 0. And therefore, the work done by G as whatever this object is about, or what you or something or is moves along this circle, is actually the integral of 0 dt, which is 0. Okay, and this should make sense because what I did here is I drew by these green arrows what G is. Okay, at this 1, 0, G is 1, 0. At the point 0, 1, G is 0, 1, right? So it's going away from the origin at every single point. And so what can I say? Well, if you are moving in this direction at every single point, like at this point, the G is the tangential component of G is 0. There is nothing. G is actually trying to push your boat from left to right. And so there is no tangential component, meaning that G is actually not doing any work at any single point of the circle, right? And that's what this 0 means, okay? This 0 is not like canceling out and eventually becoming 0. This means that every single point, the tangential component of G is 0 as you go around the circle, and therefore the work is 0. Okay, now the flux is different. Okay, so let's go ahead and try to find the flux here. Remember what flux is? This can be written, what's the best way to do this? It's negative Q d, yeah, let's go ahead and write this way. It's negative Q comma P. Remember, I think the best way to remember this is just think of this as negative. So starting with PQ, switch the order of PQ, and then put the negative sign in front of the Q. Right? So it's negative Q comma P, and then dx dy. So what is that? Well, that is, this goes from 0 to 2 pi, I guess I should say 0 to 2 pi here at this point. Okay, what's negative q? Well, here you go. This is my p, and this is my q. Q is simply y, right? So q, negative q is negative y, and p is x, right? And in terms of you know what x and y are, okay, this is negative sine of t, and x is cosine of t. Remember, x is t, and y is x is cosine of t, and y is a sine of t. So when you do this, okay, negative q is going to be negative sine, and then p is cosine of t, and the x dy, that's this, so it's negative sine t cosine of t, and that's what you're dotting. This will not be 0 for a very good reason. Okay, so this will be from 0 to 2 pi, and you get negative times negative, so it's sine squared t plus cosine squared t, and then dt, and of course that is 1 at every single point, and the answer is going to be 2 pi. And what this is showing is as follows. Try to watch and see if this makes sense. At this point, how much of the stuff is going from this side to this side? Okay, and by the way, we have this orientation, which is as you go from, well, okay, so typically this is saying the inside is to the right of your motion. So I'm sorry, to the left of your motion is inside. So whenever you try to find the flux in this way, as you go along in this counterclock direction, you're going from left side to the right side. So how much of the stuff is going from left to right? And the answer is, look at G. Okay, G is always going in a perpendicular direction to the motion, right? And it's going from inside to the outside. So at every single point, okay, at every single point, the normal component of G is exactly 1, okay? And so you're integrating 1 at every single point of this circumference of radius of the circumference 2 pi, and therefore it is 2 pi. Okay, so that's what you need to find out. Okay, I personally I was stumbling a little bit because I know this is how I showed you, negative q comma p and then dx dy. I personally prefer to do it this way. This is d minus dx. Sorry, I personally want to do it this way. It's dy and then minus dx. This is somehow I am used to doing this way, and that's what helps, I guess. So instead of doing, negative q dx plus p dy, I often do this because I remember this is my normal component. Okay, so the way I do this is often p dy minus q dx. So if that works for you, that's fine. And so I first, have to know what p and q are, right? So in this case, g was pq, and remember this was xy. And using your parameterization, you may want to write this as cosine t sine t. And then what the p is cosine of t, and q is sine of t. And, here dy, yeah, so because r is cosine t sine t, that means dy is negative sine. So no, dy is the derivative of a sine, so it's going to be cosine of t. And and then dx is sine of t. So that's, let me go ahead and write this down. Dy is a cosine of t, and dx is a negative sine of t. And so you can use all of that to calculate this. Okay, so I think that will conclude this long section too. And I think the key is really to understand these 3 types, but especially the first. Okay, and if I could, maybe I should emphasize the work integral, because we'll be focusing on that for the next couple of sections. All right, I think you have 12 or 13 questions on your homework, mostly line integrals, and then you have some work and flux integrals. And just follow what the examples that we studied in this lecture, and I think you'll be fine. All right, so I hope you'll have a great week, and I'll talk to you later. Bye.